Hello and welcome to episode 2 of Architecture of Future Tech podcast. In this volume, we are exploring autonomous vehicle technology. My guest today is Josh Siegel. Josh, would you mind introducing yourself?
Yeah, I'm Josh Siegel. I'm an assistant professor of computer science and engineering at Michigan State University, where I run the Deep Technology Lab. And our job is to make technology boring, which is different, I should note, than making boring technology. We try and work at the precipice of the possible to develop things like self-driving cars, architectures for the Internet of Things, advanced approaches to cybersecurity, and we work across disciplines and really try and be faithful to problem solving rather than to any one academic area.
Right, absolutely. And all of those things are very relevant to autonomous vehicles, which is the topic of this volume of the podcast. So before we go into the future, let's go back into the past a little bit. How did you get started? How did you get interested in vehicles and autonomous vehicles?
I grew up around the Detroit area where I was surrounded by car culture, and I saw people driving classic cars down the street and having a lot of fun with it. And so I got my first classic car when I was 14, 1955 Chevrolet 210, which is kind of like a Bel Air. And I learned about engineering from restoring that car. I learned about mechanics. I learned about chemical reactions. I learned about electrical systems. And as I got older, I wanted to keep working with cars. And I needed a car that was a little more reliable and a little safer than my 55 Chevy. So I ended up working on a 2004 Chevy Impala. And that car was really, really different to work on. It wasn't things that you could fix with a screwdriver and a socket wrench. You needed to actually program things. You needed to understand code. And that really is kind of the start of the trajectory that got me into automotive research, where I started with basically boxes on wheels that you could fix with a hammer and got into the complexities of trying to hot rod cars that had digital systems in them. That got me into working with connected vehicles, and that led me to do work now with automated vehicles at Michigan State University.
Nice. So you got started in this world very early. And we're here recording this podcast in person, which may be it's definitely the first time and may happen to be the only time I will actually be in the same room as one of my guests. And we're here in the suburbs of Detroit on a beautiful Michigan summer day. And I see something here in your room here. It looks like a table, but underneath it, it looks like an engine. Would you mind describing that a little bit and telling us what that is and why do you have that there?
Sure. You're looking at my coffee table that's made out of the engine block, pistons, and connecting rods from a Chevy 350 engine. And that was inspired by Top Gear, the TV show, but also coming across an engine block that someone had in their backyard that they were trying to get rid of. And so I pulled this out of their yard and built a table out of it. And the glass top is actually an upcycled shower door. So try and scrounge and scavenge, but absolutely, anything with wheels on it, anything with gas engines, with electric motors, that's kind of what drives me.
Right. So anything that, so you have kind of a deep affinity to anything to do with cars and engines, but also kind of being, in India, we call it jugaad, which is you make things happen with what you have, and rather than necessarily imagining what you may need hypothetically, and you kind of made something that's quite beautiful out of things that somebody else did not want. Yeah, so we're here in the Michigan summer, but let's go into a future. Since this is a podcast about future technology, we're going to imagine a winter day in the beautiful Michigan State University campus. Let us say it is snowing, and winters and the snowstorms in East Lansing can get pretty heavy. This is a future where there are a lot of autonomous vehicles on the road. Your research today has become widely successful, and pretty much every car that is on the road is an autonomous vehicle. You're standing outside the engineering building on Shaw Lane, and you see a colleague of yours, Professor Jain, let's say, and you have a very urgent message for him. And you see his autonomous vehicle coming down the street, and you recognize his face, and then you jump in front of the car and flag down the autonomous vehicle. It stops, does not skid, does not hit you, and then he rolls down the window and you're able to talk to him. So between where we are now to this future day where something like this could happen, what are all the things that need to happen before we get there?
Yeah, well, I think the most important thing is I need to have the confidence to jump in front of a moving vehicle and know that it's going to stop. But more pointedly on the tech front, in automated vehicles, we have a control loop that really is about perception planning and control. And all of these elements are fairly refined today, but they need significant advances to get to that future state. In terms of perception, for the vehicle to stop safely when it sees me coming, it needs to be able to recognize me as a person on the road. It needs to be able to navigate in poor weather situations, maybe low light, maybe where there's water on the lens of a camera, or high reflectance from laser that causes the LiDAR not to perform very well. But more than that, it needs to know that when there's a person in the scene, that person has a trajectory and be able to predict where that person is going next in order to stop, as you say, without skidding, without incident, without causing harm to the people outside the vehicle, but also stress to people inside the vehicle. In terms of planning, right, that vehicle needs to be able to anticipate what are these plausible future states, what are the other vehicles doing around it, who's in the next lane, who's behind it that might rear end it, assuming that we've got high penetration of automated vehicles, but not 100%. And then control, traction in wet weather, that's a huge concern. And it turns out it's incredibly hard to model the dynamics of traction in environments where maybe you have ice, maybe you have water, and maybe you have a bit of dry surface or some rock salt that you're driving over. So I think broadly, those are the areas where we need advances with a little bit more nuance. We need to have the compute capabilities that scale up to support a fleet that size. So we need computers that are performant, but they're also efficient. Right? We need algorithms that can take a small amount of data and derive insight from the information that they're provided. And we need advances in the sensing capabilities so that we can make better inference about what's going to happen next.
And I presume all of these things need to happen fast. You can't wait, seconds even to make that decision.
Yeah, in an automated vehicle, a typical control loop for something safety critical might take about a millisecond. And that's absolutely essential. That's how we get these marginal advances that marginal is not the right word, but it is the correct word at the same time, that take us from human capability and put us into the realm of automated vehicles that outperform humans regularly and do things that we can't. One of the things latent in this vision that you've presented, Prasanna, is if people walk in front of a car because they know it's going to stop, we've built vehicles that perform perfectly 100% of the time, or people don't necessarily know the limitations of automated vehicles. And that's an interesting area of research that's ongoing right now. There are moral and ethical problems associated with self-driving. You may have heard of trolley problems in the past, right? Do you pull the lever and cause the train to switch from one track to another and save lives, but in so doing be responsible for causing harm to those who wouldn't have been harmed if you hadn't pulled the lever? In automated vehicles, it's both subtler than that and potentially more direct than that. Right? So if you run out in front of an automated vehicle regularly and it stops every time, you create these interesting social network effects where self-driving cars never get where they need to go because nobody needs a crosswalk. They just cross whenever they want to, and cars can't get to their destination. So one of the areas that's being addressed in research now is how frequently should a self-driving car choose to delay getting on the brakes? What is a safe threshold? Should self-driving cars ever come closer to people than they have to in order to instill a healthy respect in the need of the vehicle to get where it's going? And that comes back to that planning element.
Yeah, with the mass and the velocity, there's certainly a danger to people if something doesn't go right, and they need to have the right respect and fear of that moving chunk of metal that's coming right at you.
And that's one of the big challenges, which is you never want to do harm, right? If you look at Asimov's rules of robotics, first, do no harm. But if we can instill fear while we know with certainty that we're not going to do harm, that actually can be net social benefit for automated vehicles and drive their adoption.
Right. Makes sense. So We touched on a few different topics here. Let's go a little bit deeper into some of these things that are happening. So you talked about one of the things that's happening in terms of perception is all the various sensors that exist on the vehicles today, and potentially in the future there'll be new kind of sensors that we don't know yet. How do autonomous vehicle systems make sense of this? How do these sensors turn into something useful?
An automated vehicle has hundreds, if not thousands, of different signals coming in from sensors, and they're sensors of all different types, right? We have LiDAR for light-based ranging, we have radar, we have ultrasonic, we have cameras in them. And at the end of the day, it comes down to sensor fusion, taking diverse data streams and understanding how do we get the good from one, how do we get the mediocre from another, and how do we ignore the bad from a third input. It's complicated from a mathematical perspective to fuse these sensors. There are a lot of algorithms that are largely self-adaptive if we configure them appropriately. But in essence, what they do is they say, hey, if it's nighttime, my cameras aren't very good, so I'm going to rely on LiDAR. If it's raining out, maybe my LiDAR is not very good, so I actually want to use radar. That's going to be less susceptible to the small droplets. And it does this dynamically on the fly in real time with ultra low response time. So that 1 millisecond or 10 millisecond loop.
Right. So can you talk a little bit more about what are the algorithms that are being researched, or what are the approaches that are being thought through in terms of how to do this?
Probably the most commonly used algorithm is some variation of a Kalman filter. And effectively what it does is it looks at the uncertainties of measurements from diverse sensors. And those uncertainties could either be static or they could be dynamic based on the operating condition of the vehicle. And these algorithms learn to iteratively estimate the state, predict the future state, measure the error between the predicted state and the actual next state, and then inform the algorithm's future predictions that way. And it sounds like a mouthful. If you look at the math, if you know linear algebra, it's actually not that complicated to get through, but it's updating weights and biases to say, based on what I saw just now, here's what I anticipate about my ability to trust the data from a sensor in this next coming time step.
Right. And that'll allow you to shift your focus, as it were, from one set of sensors to another. And earlier you mentioned the term multimodal sensor fusion when we were doing the preparation. Can you talk about that? Is that what we just talked about now, or is that something different?
This is one of those things in technology where it has a definition and everyone defines it slightly differently. And so I would say if you were trying to do range estimation and fusing estimates from LiDAR and radar and stereo cameras, that is not true multimodal in the sense that, maybe we add GPS to the mix for it. Maybe we add an accelerometer to estimate our own state. And that adds new dimensions of the measurement to it, where it's not just about looking outwardly from the vehicle. It's not just exterioceptive sensing. We have something proprioceptive as well, measuring inward to understand how our weights and biases change by our own operating state. Right? The faster we go, the less we want to trust slow update rate cameras in a vehicle, for example. And I think you will find a lot of people who say that multimodal is any two types of sensors, even if they're doing ostensibly the same thing. I like to think of multimodal as really being sensors in different domains being used to get a better, broader picture of the context of a vehicle and its environment.
So this may be even more immediately required before we get into a full autonomous vehicle AD world. There is a ADAS world, which is a driver-assisted world that we are in already and are making some progress towards. So when you have a potential driver and you have a system that is sort of can do certain things, but not everything in terms of driving automatically, there you may have to deal with in-cabin sensors, looking at attention, looking at gaze detection, focus on where is this person paying attention to? Are they looking at their phone? Are they talking? Or is there a loud child in the back seat and they're distracted? So and being able to add that into the kind of external sensors that we talked about, or the kind of sensors that are about driving, to then realize that, okay, essentially here the driver becomes one AI system in a way, or HI system, where the AD system decides that, you know what, I don't trust the decisions taken by this human anymore because of these things, at least for the next few minutes, and I'm going to be extra watchful. Is that one of the ways that multimodal sensor fusion is going to work?
That's part of it, right? And if you have a human driver behind the wheel, especially in the near term when we've got ADAS versus full automation, you've got these issues of drunken driving, drugged driving, drowsy driving, distracted driving that we need to solve for. And these biometric sensors absolutely play a huge role in that. I would say one of the biggest challenges in automated vehicles is not about the core technologies so much as human interoperability and human handoff. Handoff being the notion that if your car decides it can't drive itself because there's too much rain and the sensors don't work, or some component fails and it doesn't have a fail-safe module, a human needs to take over control of that vehicle. And as it turns out, right now we get about a half second to 1 second of handoff notification, and it takes a human 45 seconds to a minute to resume stable control of driving. Now, grapple with that as you think about, if we're doing double integration to figure out our future positional states, and you do that once every millisecond, and you're doing that for a minute, if you have 0.0001% error, you're going to be hundreds of meters off by the time you get to the end of that minute.
Right.
And so you don't know where the car is going to be, but the person also isn't able to resume control. And that really is the big barrier now, that we don't know what we don't know, and that humans who don't understand the capabilities of their vehicles are not ready to intercede and take over because they know that some dangerous scenario might be coming up. And to the broader point of interoperability, if you had automated vehicle technology today and you had policy that said, let's get all the cars off the road, let's take 2 years to build this out, we've got the investment that we need, I would say self-driving is largely a solved problem, but it is the fleshy meat bags behind the wheel and outside the car that are irrational agents that are hard to model for. And I say that as someone who, you'll never take my keys away. I've got my classic cars. I'm going to keep driving them. But it's not only the technology that's the problem. It's the technology interoperating with the humans. And to close the loop, right, that's where multimodal sensing does come back in, that we need to understand inside the car, outside the car. Can someone resume control? Are they being attentive? Is someone going to jump in front of the vehicle? And if they jump in front of the vehicle, how far are they going to go into the road?
Right. And you talked about compute. So you need to make these decisions fast. You're using Kalman filters, which aren't, from a linear algebra perspective, not super complicated. But as time goes on, the kind of decisions that need to be made in vehicle, at that instant, within a millisecond, they start becoming more and more complex. And so what kind of compute do you think we are going to see by the time this reality, this vision that we had earlier, becomes a reality? What is the kind of compute power that you think will be in a car?
Compute for automated vehicles is already changing rapidly. We've seen a move from few core high power systems to multi-core low power systems. And certainly for deep learning, that is one approach that makes a lot of sense. Increase the core count, run more operations in parallel. And frankly, get compute that doesn't always return the right answer 100% of the time, because effectively what you're doing is you're predicting multiple future states, weighting them, and figuring out what's most likely here, or what's the average best outcome. More broadly than that, more broadly than going parallel compute and high efficiency compute, we are seeing the beginning of an era of the software-defined car. And some of that compute is actually taking place in the cloud or at some remote computing environment. So we're seeing a split between latency critical operations, things where you're responding to a stop sign or someone jumping out into the road. And then we're seeing these latency insensitive operations like route planning take place perhaps outside a vehicle at some data center. That is probably 3 to 5 years on the horizon. But as we see increasing uptake of autonomy, as we look at things like federated learning, learning from fleets writ large, right, that's going to play a very significant role, I would say.
Right. And so you're looking at compute happening not only in vehicle, or maybe even you go one level deeper and say there's a bunch of compute that happens on a per sensor basis or per area of a vehicle, per zone, all the way to what I've been hearing the term fog compute, where you're looking at it's not really full cloud as in some central cloud, but there is a distributed part of a cloud that exists. Maybe it is part of the infrastructure, maybe it is part of a peer-to-peer network that can be created by several of these vehicles together. And all of these things are making rapid progress, but one of the concerns that I keep hearing about is the heat. Is that a challenge? Energy consumption and kind of the heat output of this as being one of the things that need to be solved.
So, first, to the point of fog compute, I would say we have a lot of that already as we think about building connected and automated vehicles. Automated intersection management systems that coordinate vehicle passage without traffic signals exist, right? And that's done with an intersection controller. You've basically got a server running at every four-way intersection or more that coordinates vehicle traffic through it. So, this paradigm is already out there in industry, both in research but also in practice. To the point of heat and energy efficiency, self-driving is not mining cryptocurrency. There's a lot of heat generated. There is a lot of deep learning going on, but it's not heat for the sake of heat. And read into that what you will. But the heat generation from the compute in vehicles is not a problem. What is a problem is actually the energy consumption. Because if you've got an electric vehicle and you're trying to power compute for self-driving in it, that's a significant percentage of your battery capacity that goes into the self-driving versus actually propelling you forward. And this is an artifact of two things. One, electric vehicles are incredibly efficient, and so it doesn't take a lot of watt hours per mile, but also the compute in the vehicle has not been optimized up until very recently to not use a lot of power as your car drives down the road. And so what you're effectively seeing is this nearing of parity of your motive energy and your compute energy in a vehicle. And I think that will need to change in order to drive adoption of electric vehicles, which, because they're natively drive-by-wire for the most part, will drive adoption of automated vehicles. And it becomes this virtuous cycle.
When you talked about a server in every traffic signal, that got me thinking, every movie that you see where there's a hacker that kind of evil hacker is trying to disrupt something, or there's a bank robbery and somebody is going through and they have a hacker who is changing traffic signals for the benefit of whatever evil plan they may be hatching. From a security perspective, does the distribution of decision making and compute to so many places simply create a very large surface area that you now need to secure? What are the challenges that you're seeing from a security perspective in this world?
Yeah, so I think Fast and Furious is a great movie franchise, and they get a lot of things wrong, but some of the hacking they actually get close to right when they're doing signal control or when they're doing some of the car hacking in the earlier movies, at least. Right? I think your point is right that these are honeypots. They're large attack surfaces. They're hard to secure. They're critical infrastructure. And bad actors go after those systems more than they would go after systems that are smaller impact or more tightly secured. I always come back to, when we talk about car hacking or infrastructure hacking, this idea of, is the hack that we're talking about really the easiest way? And when we talk about hacking controller area network, the network that kind of makes your car run, it's hard to hack that, but it's easy to cut a brake cable. And I think that's where I am on the intersection management as well. Could it be a problem? Yeah. Could it be a huge problem? Absolutely. But there are easier ways to sow discord and chaos, right? And I think that is my bigger concern. It's the people who willfully run the red lights, not the people who hack the intersections. In the same way that I'm not even worried about people cutting brake hoses, I'm worried about people who don't inflate their tires properly, because way more accidents are caused by poor vehicle maintenance or inattentive driving than would ever be caused by this sort of malicious attack.
I guess the news, though, is going to talk about, there's a particular vehicle that was hacked in under 12 seconds while it was driving and it was stopped. Or you look at the enterprise kind of data leaks and so on. And security is certainly something that creates a lot of concern among people, regardless of whether it actually causes a rise in accidents or not. Is there something that the industry is doing or is not doing that should be done to take away at least the low hanging fruit from a lot of these areas? So from what I've seen in the past, when it gets into devices, once they work, people stop looking at it beyond that. So you had the early the electricity meters had basically no security, and anybody driving by could read your electricity consumption. And now that's not the case anymore. So simple things like authentication, not using default passwords, encryption of the things, or of the data that's going through, or even just needing a key to be able to access certain functions of a vehicle, and not just like the same key that every dealer in the whole world has.
So I have to be careful how I frame my response because I work with the auto industry closely, and they've funded me in the past, and I hope that they will in the future. And what I will say is their hearts are in the right place. And there are definitely standards that are being worked towards for connected and automated vehicle security. The security landscape within automotive is a million times better than it was 5 years ago, is a million times better than it was 5 years before that. Yeah. And I think it is a significant concern, but it is being thoughtfully addressed. And I'm hopeful that best practices will catch up with vehicles soon. I think the broader point that you raise is that people see something on the news and they freak out. And part of security culture, part of security hygiene is educating oneself on the capabilities of their devices, good and bad. And I would bet that almost all of your listeners, if not all of your listeners, have never read through the end user license agreement for their vehicle. And I would lay money on the fact that all of your listeners have not read it for their friend's vehicle that they've been a passenger in. And their friend's vehicle, right? It's still got controller area network. It's got sensors. It's got inward facing data streams that know who's in the car, where they're sitting, what they're listening to on the radio, where that vehicle is. And because of something called a click wrap agreement, when you open the door, even if it's not your car, you get into a vehicle, that data goes somewhere and someone has access to it. And to me, that's far more concerning than the security issues that people raise, because you're willfully giving all of your personal information to, whether it's OEMs or third parties, someone, right, that you don't even think about day to day. And that in aggregate is a far larger issue, I think.
Right. You get into implicit consent at that point, and you
Exactly.
need to turn that into how do you actually say that, okay, this is my data, I do not allow you to use it, and homomorphic encryption maybe, or some other techniques to do that someday. Yeah. So one of the things that I find interesting about autonomous vehicles is the assertion that an autonomous vehicle needs to drive safely for, I don't know, 8 billion miles before it is considered safe. Before an autonomous vehicle gets its driver's license, as it were, it needs to show that it can, drive 8 billion miles without crashing anything. I don't know about you, but I didn't need to drive that much to show that I can drive. How do you think this is possible for, in the amount of time that we have, for cars to actually drive that much and kind of demonstrate to regulators that they have met the safety criteria?
For regulators, it's easier to say no than to say yes. And sometimes you just make a goal so hard to reach that it's effectively saying no, because then you're not responsible for the outcome of it should it come to pass, because it's not likely to pass, right? I think that your point is valid, that we hold self-driving systems to a higher standard than we hold human drivers. And I don't frankly think that is to the benefit of society. I think it'd be better to get drivers who are not comfortable driving off the road. I think that there are plenty of people who drive out of necessity who don't want to, who are hazards potentially to themselves and to others. But latent in that question is, how do we get these miles, right? And some of it is in reality, and some of it is in simulation. Frankly, most of it is in simulation. There's also the question of where are we today versus getting to that 8 billion mile mark. And if you look at data from 2021 and look at miles for disengagement, with disengagement as defined by manufacturers themselves, the best of the best are doing about 40,000 miles per disengagement. And that's actually pretty close to on par with average human performance right now. So on the one hand, we've largely matched human performance before having scary events happen. On the other, we've got this big number that we're trying to get to that we may never in reality, but we can use simulation to catch up on that. But maybe the real question is 8 billion the right number? Is there some number? Is there some other way of evaluating both what I would call local and global welfare for automated vehicles? If you are a safer driver than an average automated vehicle, maybe you should be able to keep driving, but that's inequitable. So if we put automated vehicles out there, maybe you are in a slightly less safe vehicle, but we get more vehicles out to more people that are safer than their average driving. And so net, we save lives, we save time, we save efficiency. And, that really is one of the big questions that companies now are struggling with, and legislators, of saying, when is enough enough?
Right. And so, from a regulatory perspective, one of the things that I've been thinking about is how do we move from essentially a deterministic uh, list based regulation to a more probabilistic regulation? But I think what you're saying is it's not just probabilistic, but it's also adaptive. It's also adapted to the person and the situation that you need to be in. And autonomous vehicles may be safer in certain situations in the hands of certain people than others, which if I'm just thinking from a regulatory perspective, it's hard enough to go from deterministic to probabilistic, and now you're saying now customize it, make it adaptive to each person. That sounds like a challenge in and of itself.
And it doesn't even have to get that granular, but the reality is driving is very different around the world. If you travel to 10 different countries and drive, you find that the rules of the road are very different, but also the way that people follow the rules of the road is even more different. And it does kind of get down to that at the zip code level in the US, right? We've got these little tiny pocketed regions called zip codes that are maybe 5 kilometers by 5 kilometers or smaller. And when you cross from one into the other, maybe right turn on red is legal in some places and it's illegal in others. And the way that we stop for school buses, even though the law is the same everywhere, it varies from one zip code to the next. And, evaluating AV, automated vehicle performance, is very different, not only for the individuals, but how they perform in these regions. Go to Boston, people drive on the shoulder of the highway during certain hours of the day. That's the scenario that people don't train for in Michigan if you're building a self-driving car. If you are training a vehicle in California, it's got to deal with wildfire smoke, but it doesn't deal with snow like we get here. And so all of these are big challenges, and that's why there really is not going to be a one-size-fits-all metric anytime soon.
Right. When I was talking to one of our colleagues in Germany about autonomous vehicles, and there was a lot of optimism that given how the roads are, that we're close. And I said, okay, now let's bring that same box that does autonomy well in Germany. Let's bring it to India and see how well it performs. And it's a completely different dynamic. And that was kind of a moment of like, yeah, we haven't even thought about how to drive in India or Lagos or wherever else where the traffic is notorious. So one way to do this, you talk about simulation, and one of the ways to simulate a lot of these different situations is instead of sending cars everywhere, you can do that in simulation. You've done some interesting work in simulation in the past. Can you talk about that briefly?
We've done 3 simulated studies in the Deep Tech Lab, and 2 of them look at the human factors of self-driving, and the third really looks at how do we develop better algorithms. For human factors, we developed simulations that actually try to figure out what's the optimal level of scared that a pedestrian should be if they try and cross in front of a moving vehicle. And we conducted a survey with that. We had a game where people knew that vehicles either were or were not automated, or sometimes we surprised them by not indicating. And we had them cross the road as quickly as possible to get the high score, and kind of saw if they had knowledge of whether or not a vehicle was automated, would they take different risks around it. We saw that as people became familiar with autonomy, they would take more risks around that vehicle, and net might actually become less safe as a pedestrian and impact the transit time of that vehicle. So we're continuing to do work in that to figure out kind of how do we optimally strategize indicating that a vehicle is automated, that it sees you, and then how it responds to you as you're crossing. Another study that we are launching now looks at the trolley problem and looks at ethnographic elements of it. How do you respond to different moral and ethical dilemmas based on your own background? But I would say the most interesting from a marketing perspective or an outside view perspective is that we've done work on adversarial self-driving. And when you grew up, if you learned how to drive, someone might have told you, drive like everybody's out to get you. Certainly in Michigan, that's something that you hear in driver's education, right? Drive like everybody's out to get you. And we actually built this in simulation. We created a coupled network of reinforcement learning agents where we had a protagonist who tried to get to their destination and an antagonist whose job it was to keep you from getting to your destination. And we ran this for a few thousand cycles. And what happened was, over time, the protagonist got better at avoiding the antagonist got better at hitting the protagonist. But when we took the protagonist and put them in a non-adversarial environment, they were able to avoid all sorts of incidental collisions. Someone who's not keeping their lane well, someone who is drowsy behind the wheel, who might drift in front of the vehicle. You can dodge that. You can anticipate that a lot better. And so we haven't done billions of miles. I would say we've done thousands or tens of thousands of miles, but it demonstrates the potential to test things in a virtual environment that we would never be able to in real life.
That is very interesting. When I was learning to drive in Michigan, nobody told me that. Nobody told me to drive like everybody's out to get you. But I think when I was learning to drive in India, that is definitely what I was told to do, is to kind of just assume that they're trying to run into you. And how do you keep going? So I think with that, we can leave our audience with that thought: drive like everybody's out to get you. And if you're listening to this podcast while driving, this is the absolutely perfect time to ask you to do that. So thank you very much, Josh.
Yeah, thank you for having me.